Hi, my name is David McCallen. I am a professor in the Department of Civil and Environmental Engineering at the University of Nevada, Reno. I am also the director of the Center for Civil Engineering Earthquake Research. And I guess finally I would say I'm a local. I grew up in Truckee most of my life before I went off to the University of California. And my first college experience was at the University of Nevada, Reno. When I was in high school, I drove down from Truckee every day and took my calculus class and drove home. So I've got a long association with the University of Nevada. And I tell a lot of my colleagues here at Nevada that I predate them at the university. So I'm a real local, and I really have an appreciation for the area. And I think it's a beautiful and wonderful area. And I'm really happy to be with you today. Are we good to go, Dave? Wonderful. Well, look, I wanted to start, when I first came into this meeting early on to check out the IT, Dave and I were chatting a little bit about our common experience with the Loma Prieta earthquake in California. It turns out we were both in the proximity. He was in Pleasanton, I was in Livermore, and I was working at Lawrence Livermore National Laboratory at that time. But I've got a better story. My story starts in 1966 when I was a young man, very young man, actually a very small kid, growing up in Truckee, and there was a magnitude about 6.6 earthquake that occurred near Stampede Reservoir. And many of you probably know where that is. I had no idea what an earthquake was, and I was so little, and it scared the bejesus out of me. And we had aftershocks associated with that earthquake for many, many weeks. But honestly, it started a lifelong fascination for me with respect to earthquakes and the raw power and the phenomenology of earthquakes that haven't subsided throughout my entire career. And it put me on a career path, frankly, to be involved in this area. And I took an engineering career path. I went to the University of California, Davis, went on to Livermore Lab. And I've been at UNR for about 3.5 years now. And it's wonderful to be back in the area. And I'm really excited about being at UNR. For today's presentation, I really wanted to focus on two things. I know a number of you are familiar with some of the capabilities we have in the Earthquake Lab. So I'm going to talk very briefly about the legacy of excellence that we have in earthquake engineering here at the university. But then I would really like to shift gears, and I would like to talk about some future coming attractions and things that are very exciting to us. And that's in terms of future directions and future capabilities that we're in the process of beginning and building in the Earthquake Lab to really keep us at the cutting edge and relevant in this field and in a leadership role. So I'm going to speak to both of those things. And I'll begin by noting, and some of you who have visited probably know this, that UNR has been long recognized for tremendous expertise and contributions in earthquake engineering. And this really predates me, but it really has been well known. And if you've been on campus and you've seen our facilities, you realize that we have two very large laboratories. We have the Large Scale Structures Laboratory on the left, where today we tend to put large-scale specimens and push and pull on those specimens statically and break those specimens so we understand the capacity of those specimens. That is going to be the home of our new large-scale laminar soil box. And I'll explain in some detail what that means. It's an important new capability. On the right is the Earthquake Engineering Laboratory. And I think a number of you have probably been on tours here. It's a little odd for us. We tend to have a lot of tours, and we haven't for a year. So it's wonderful to be able to reach out to the community and engage you again. And I would argue, consider this a rain check. We're going to have some new capabilities, and we'd love to have you in and watch us shake and bake things in the future. So today's a virtual tour, but I hope you'll look forward to visiting us in the not too distant future. In our Earthquake Engineering Laboratory, as many of you may know, we have a large number of hydraulic shake tables. And these are very carefully controlled tables. You can see we have 1, 2, 3 here in the laboratory. There's a fourth over here that's hidden. These are hydraulically driven. We can program these to generate representative earthquake motion. So we have a very sophisticated control system. We have a control room over here, and our technicians and our laboratory staff can pull up an earthquake in digital form, a time history of an earthquake, and we can program these tables to reproduce that earthquake. And so what I tell people fundamentally, what we're really good at making earthquakes in our laboratories. And why is that important? Well, it's extremely difficult to get good earthquake data in the field. It can be done, but that earthquake data is very sparse. Why? Because we can't predict with any fidelity when the next earthquake will occur and where. And so we tend to go out and instrument structures in the field, but those may sit there for years. They may sit there for decades. They may sit there forever and never be subjected to an earthquake. So in the laboratory, we can take earthquake components, structural components, and subsystems, and we can put them on our shake tables, and we can subject them to very precisely controlled earthquake motions. Moreover, we can repeat those motions. So we can look at a structural design, we can shake it with a motion, we can change that design, try to make it more reinforced, and we can shake it with the same motion to validate improvement or not. And so it's a very, very important capability to be able to shake things with simulated earthquake motions in the laboratory, quite important to the earthquake engineering community. UNR, our original facility, was built with support from the Federal Highway Association with bridge structures in mind. And so the notion of having these multiple shake tables was it allowed us to put multiple support motions, different support motions, across a large representative bridge type structure to understand the effects of phase motions. And one of the really nice tests that was done by Professor Buckle years ago, and I'll show you a little snippet of this, you can see our technicians up on a curved bridge that was built in our laboratory. And oh, by the way, those are vehicles, brand new vehicles on top of that particular bridge structure. And the focus of this test was to try to understand the phenomenology of how a bridge responds when it has vehicles on it. Vehicles have damping systems, they have suspensions, they have a dynamic system all their own. And there were some fundamental questions about how cars and vehicles on a bridge would actually impact that bridge. So this is an example of the types of challenging tests that we've done historically to really aid understanding and ensure that our structures at the end of the day are earthquake resistant. No such thing as earthquake proof, but earthquake resistant. It's a little loud, but I'm going to show you an example of what that shake table test looked like on the next video. So bear with me as it gets a little noisy.
Whoa. Oh my God.
So this is just one example of a test. Now, I don't know about Dr. Buckle, but that audience looks a little close to me to that test. And after I saw this video, I coached him about that the other day, and he had a supreme confidence based on their first series of tests that everything was going to be okay. But that's an example of the type of complex tests that we do. We have a number of key stakeholders that look to us to help solve their challenging problems. I'll point to two. The one on the left is some bridge column work we did for the California Department of Transportation, where they wanted to understand the ultimate capacity of some of their bridge columns. So we could build those columns in the laboratory, connect the hydraulic ram that you see in the upper right-hand corner, and push and pull on that column to determine what the ductility of that column is. Not just the strength, but the ductility. How well can that column absorb energy and not break in brittle fashion? So that's one example of our stakeholders. It's NDOT, a whole plethora of various state agencies. On the right, and something that's become even more important for us, are federal sponsors. And the Department of Energy has been a very large sponsor of ours, as you'll see today, over the last 4 or 5 years. And this was a test of a very large column that resides, a type of column that resides in a very critical, one-of-a-kind facility at Los Alamos National Laboratory. It was a very important mission-oriented structure, and they absolutely wanted to ensure the integrity of that plutonium facility at Los Alamos. So they really wanted to get a good handle on the seismic resistance of their facility. So we, in fact, built and replicated their columns in the laboratory and pushed and pulled on those columns to determine the capacity of those columns as well. And so the point is, we do a lot of work for a lot of sponsors, and we're typically solving critical problems and answering unanswered questions and determining what the strength and capacity of those structures are. So that's been the rich history of what we've done here in the laboratory. What I really want to focus on today, though, is our new strategic directions and opportunities, and share those with you. Things we're really excited about. And what I'm showing you here is our traditional, in these boxes, our traditional area of large-scale earthquake experimental testing. And that's really been our forte for many years. We are adding to that with a very new facility that's being supported by the Department of Energy. And so a significant portion of my talk today is going to be focused on a new experimental facility that's going to be tailored to understanding something called soil structure interaction. And I'll explain what that is in the next couple of slides. In addition to that area, we're looking towards new things that we can be at the cutting edge of. And one is an advanced computer simulation, the box in the lower left-hand corner. And as many of you probably know, high performance computing has just been on a tear the last 2 decades, and that continues. And so people are building ever faster and ever bigger computers, which allows us to model and replicate things from an earthquake sense in ever increasing detail with ever increasing fidelity. So it's really important that we be to some degree on the cutting edge of advanced simulation as well. And then finally, on the lower right-hand corner, there's an emerging area called structural health monitoring or intelligent infrastructure systems. And historically, if people wanted to understand the condition of their facility or their structure, they'd send out some technicians to walk it down and take pictures and take notes and visually inspect things. Well, imagine if you had an earthquake and you need to know as a businessman or a stakeholder, do I have to evacuate that facility, or can I continue operations in that facility? Imagine if you owned a hospital and operated a hospital in San Francisco, like at UC San Francisco, 800-bed hospital, and there were an earthquake. You're faced with some critical, time-intensive decisions about what action is appropriate to take. So there's a whole new area that's expanding, and it's leveraging off the advancements in rapid communications in the Internet of Things to allow rapid sensing and automatic determination of some of the condition assessments of facilities after a major earthquake. So that's a new area for us too that we hope to get involved in. What I've shown with the red arrows is if we play our cards right and plan this strategically, all of those things I show on this graph are interconnected. They're all related. We can use simulation to predict our experiments and design our experiments. We can use our experiments to confront the accuracy of our simulation models, for example. And so they're all at some level interconnected, and we're moving forward in all 3 of these areas. So I will avoid technical jargon as much as I can, but there's one term that I really need to dig into and frame and describe to you just a bit in order to validate what we're doing in this new large-scale facility. And that's the phenomenon of what's called engineers call soil structure interaction. And imagine if you have a very, very large or massive structure or embedded structure, and the earthquake waves impinge on this facility and the ground shakes. Well, these structures that we're concerned with can have a significant interaction with the supporting soil. And that's shown in this cartoon. The structure rocks back and forth, and it can deform the soil and cause interaction with that soil that is very complicated to characterize and model and understand, frankly. And so some of our most important structures have to account for this type of behavior. It's very, very difficult to get a comprehensive look at this type of behavior in the field because it's hard to instrument the subsurface and understand how the ground's deforming. We can generally instrument a superstructure, but look at the full coupled system is really, really problematic in the field. So we've got to think of a better way. So what we are pursuing in concert with the US Department of Energy is to be able to replicate how soil behaves in the field in a laboratory. And the way we're doing that, if you think about this plug of soil in the field when an earthquake hits and how that responds, we want to design a system in the laboratory that precisely replicates that type of behavior. And this is a lot harder than just getting a big giant soil bucket and filling it with soil and shaking it. We have to have a very specially designed soil box so that the deformations and the way that this big plug of soil behaves in the laboratory is identical or as close as we can make it to how it behaves out in the field. Turns out that because of the characteristics of soil, we have to have a very, very large soil mass to do that appropriately. Because soil, the constitutive behavior or the way soil behaves is dependent on the overburden of the soil above that confines that. So we have to have a large bucket of soil that we then have to shake. So this was the cartoon when we first rolled this idea out to the Department of Energy about 4 or 5 years ago. So there has been a very intense design effort by my colleagues in the Department of Civil Engineering that you see over here. And this was our concept. And after a great deal of design, this is our reality in the facility that we've actually designed. So the concept goes as follows. This is a very, very large, what we call a laminar soil box that has behavior that can replicate the behavior of that soil in the field. And it's very, very specially designed. And I'll go into a little more detail on this. You can see these little white things here. Those are rubber isolators or rubber bearings. Just think of a big rubber washer, if you will. And so we have metal hoops, hexagonal hoops that are connected through these rubber washers. And the reason we do that is so that we can make sure that this particular slug of soil, when we shake it, behaves very similarly to what that slug of soil would behave like in the actual field. We put that big bucket or laminar soil box on a big steel platen that is floated on hydraulic bearings. So this is on hydraulic bearings that allows this whole assembly to move back and forth very easily. Then we have giant hydraulic rams, what we call hydraulic actuators that are hydraulically driven. They react off these massive concrete blocks and they can shake the table and thereby shake the whole soil box. We can put a structure on top of the soil and we can replicate these earthquake motions. We can put a bunch of sensors above and below the structure on this and really understand the complex interaction between the soil and the structure. This will be the largest such facility in the United States by a large margin. And there's a facility about this size in Japan that does similar work. So this is going to really be a unique capability within the United States. This is just another view of that in profile that gives you a little better look. You can see the reaction blocks, the actuators. These are the hydraulic bearings I'll show you pictures of in a moment that this table basically floats on. And we have 408 of those elastomeric bearings, or if you want to think about it, little rubber washers within this wall. And then you can see that they're graded in a very special way so that they're not just uniformly distributed so we get the right behavior. So that's another picture of our assembly. We couldn't do this without our commercial partners from Reno. Reno Ironworks has been a longtime partner for us and many of our fabrication activities, and they played a central role in developing this soil box here. So what I'm showing you here is up at the Reno Ironworks facility where they are putting together that big platen or table that this rides on. And it's a very carefully designed big hollow box with all of these webs that you can see here. You couldn't make this solid, it would be too heavy. So we have to have a honeycomb structure, a very well-designed honeycomb structure. And this is just one element that you see being welded up at Reno Ironworks. Then of course they delivered all of the assembly. So now we're looking at, up in this cartoon in the right, this is the steel platen that the soil box rides on. And you can see the final fit up of this with the Reno Ironworks workers in our laboratory. And this whole assembly weighs about 100,000 pounds. And you can see it came in 9 segments and they had to fit and finish this very nicely. And I can tell you this came out with a perfect and exceptionally flat fit up. So they really delivered for us. It's not easy in welded structures because of all the heat and the welding to prevent deformation and warping. You have to be very, very careful. And this just came out with a marvelously flat surface. So kudos to Reno Ironworks. They did a tremendous job. And our project couldn't have gone forward without that contribution. There's a company called Dynamic Isolation Systems out in the business park east of Reno. And they are world experts in generating and developing bearings. That's what they do as a major part of their business for seismic isolation. So they were instrumental in making the bearings. And this is a close-up picture of some of the bearings in the steel tubes in our box wall. But they had to make bearings at a rate that they haven't done before. We needed 408 of these. And you know, the secret sauce in making bearings is the constituency of the rubber. And it's even worse than a recipe. And a family recipe that nobody will tell you about. They have secret recipes for their bearing rubber. And so they have to accommodate this large of throughput for the bearings, they had to cure these bearings in mass. So they came up with some jigs so that they could pour the rubber and cure these bearings in series and resulting getting 408 of those for us in a reasonable time frame. We had to qualify those bearings. So we would take out a sample, we would bring them down to our laboratory and push and pull on those. To validate those, but this was a tremendous effort to develop those bearings. So this is what they delivered. And so you can see outside of our laboratory here, shrunk wrap, these are all of the constituent components of our soil box, palletized and covered with plastic. And for scale, you see our 2 lab technicians here. So this, just the creation of the components of this box was a tremendous, tremendous effort. And again, another local business that really delivered for us, and kudos to Dynamic Isolation Systems. Then we had to pull and put the box together. And this is the box going together in segments in our laboratory. You're seeing a box segment that is dangled down from our overhead crane. So we build these in about 5-foot chunks, bring these over and connect these. And this is an example. This is the completed box. And this picture is deceiving because it's a lot bigger than this when you stand next to it. And if you can make it over, we'd be happy to show you that box someday. This particular picture over here gives you a little better perspective with one of our technicians here. This one's a little deceiving, but now you can really see that specialized design with this very carefully analyzed and distribution of the rubber bearings within that box. And so the box has to resist more load near the base, so there's more of them, and then it gets, we want it to have a pure shear deformation mode, so we reduce the number of those bearings as we go up in the box. So this is what you see. This is the action item that you see here, and this is where the soil will go. 20 small dump trucks of soil will go inside this once we fill this up, and then we'll put the structure on top on the outside. So then that's not all. We have to look at our other components, and what you see here are those giant reaction blocks that I was talking about that we have to react off of with our hydraulic actuators. So we have a very deep 3-foot slab floor here, but these reaction blocks have to resist when these hydraulic actuators start pushing on the soil box. They have to react off something. So they have to react off of these reaction blocks. So we brought in 16 cast massive concrete reaction blocks. We drilled down through the floor and we put steel rods down through and bolted all these to the floor. And you see the scale of these. This is one, the reaction blocks at one end are shown here. The reaction blocks at the far end down here are shown here. Then the actuator plates are connected through these aluminum plates to that box, and then they drive the main soil box. This is a big, massive, box that we're going to shake that's full of dirt, but there are still extremely precise alignment and precision requirements for this box. I mentioned the box is floated on hydraulic actuators. If the pads that the actuators are operating on are not level or they're tilted, you can't float that whole giant dynamic system efficiently and get it to be, very, very soft and weak so that the actuators can drive that box. So that requires a very precise alignment of the whole system that supports the box. So what you see here are our lab staff and our technicians putting in and precisely leveling all the reaction plates that those hydraulic actuators are going to slide on. So in the center, we have a rotating laser, and we have a sensor out here, and that laser rotates, and we can precisely adjust and determine the leveling of all of these pads. So even though this is a very massive rigid system that we're going to be shaking very hard under earthquake motions, it has to be very precisely aligned and very precisely set up so that it floats just right. So it's somewhat temperamental in that standpoint. There's not a lot of people in the world that can do this. We're lucky to have a very, very experienced team in our laboratory that have built these shake tables before, and I'm telling you, these folks really know how to do this. So it's a tremendous advantage to us in being able to build these types of unique facilities. So I'm going to end with saying we are, for this segment of the presentation, we're in the home stretch. And this is Dr. Patrick Laplace, who's standing in the middle of where the shake table is going to reside. You can see now the reaction blocks. You can see each 250,000 pound actuator. These are slanted at an angle because we're going to be able to shake this with what we call biaxial or earthquake motions in 2 directions simultaneously. So you see 8 of these massive actuators. These had a lead time of over a year, so we had to outline our procurements well ahead. This is not hardware that you just bop down and get in rapid delivery, just-in-time delivery. We had to supply chain all of this hardware, and these were developed by MTS, a major vendor. And so all of this stuff had to be, set up schedule-wise in a very carefully aligned procurement process because of the lead time. These are semi-custom items. Now you can really see here the reflection and how smooth these plates are, where the hydraulic actuators ride. So each one of these hydraulic bearings, has a thin sheet of oil and will slide back and forth on this very smooth plate to get as close to frictionless as we possibly can. So all of our energy goes into shaking the mass of the box, not overcoming the friction that occurs at the contact points. So again, these have to be precision aligned and they have to be as close to frictionless as we can possibly get, so that whole giant platinum box are floating vertically, and then we can easily shake it with the actuators and generate the types of strong motions that we would like to. So even though we're moving a big chunk of dirt, there's a lot of very careful precision activities that are associated with doing this correctly. And so this was a major design effort. So that's our facility. We are on a time frame to complete construction in the July or August time frame, and then we will go into what we call commissioning. And you can imagine, just like somebody building a submarine or an airplane, you build it and then you go commission it. You don't just start using it from day one. You have to test the operation of all the systems and make sure everything's working as intended. So we will go through a major commissioning activity in the after July and the August, September timeframe. And then we'll really be excited because we'll be able to move forward on some of the first experiments in this really unique facility. And it will, in our view, yield new knowledge and new understanding about soil structure interaction and help us design even safer structures, accounting for the effects of the interaction between the structure and the soils in a way for the first time that we can do experimentally in the laboratory that we couldn't do before. So this is a very important development for us. However, I want to mention a couple more things. I mentioned the increases in speed and high performance computing. I'm showing you a simulation on a massively parallel supercomputer at Oak Ridge National Laboratory that was done by our colleagues and some of our folks here at UNR at Lawrence Berkeley National Laboratory. And this is simulating at regional scale a giant computational model of a magnitude 7 Hayward Fault earthquake occurring in the San Francisco Bay Area. The computational model encapsulates the whole Bay Area, as you see here. That model has 200 billion grid points, and we're using what's called a finite difference grid to model the wave propagation in this area. And so this is simply emblematic of how far computations has come and how we are harnessing these large-scale simulations to really better understand earthquake phenomenology, both from the standpoint of the earthquake ground motions and how those ground motions vary in a complex fashion across the region. And also, in what we're doing here at UNR, which is quite important in our students, is we're understanding how these earthquake waves interact with a building or a structure. So you're going to see on the left, this is a simulation of an earthquake. Those are the earthquake waves propagating away. And we are coupling our soil and building model on the right to that geophysics model on the left, so that we can really replicate in simulation space how those earthquake waves interact with that structure. So this particular simulation was done by a PhD student, my PhD student, Zhenfei Wang here at LB&L, and a geophysics student, Eric Eckert, master's student in geophysics. And so this goes to my point of enhancing our simulation capability and having a cutting edge simulation capability that really will very nicely complement and augment our ability to do experimental testing. And when you do these types of things on a computer, you learn a lot. You can play the what if game. You can look at different earthquakes, different rupture scenarios. You can look at different buildings, different design of buildings in a very efficient way, and then link that to the experimentation in the laboratory to validate some of the effectiveness of the structural components and how things behave. So that's a tremendous, important new capability for us. I'm going to end it with the last area of intelligent infrastructure. And this is really the area that I mentioned early on about an opportunity to exploit this tremendous advancement in communication technology and the Internet of Things that is coming. And so we have been working on developing some very specialized sensors that will allow us to have a building that is in essence, a self-monitoring building. And so an earthquake occurs, we are going to have sensors in that building, and I'll talk about our first deployment in a moment, that will communicate with wireless RF communication so we don't have to drag cables. So the sensor will measure what's called interstory drift in a building, and I'll talk about that in a moment. It will communicate that to a central node. That'll go up to a gateway, and that gateway will either communicate out through the internet to distribute that data very rapidly to a response center, send an email notification, or even send data to a phone app that you can get remotely. That will be one avenue. Or alternatively, if the earthquake is so bad that the internet is down, we're going to have an option to blip data up to a satellite through an Iridium satellite connection, so we can always reliably get that data out. So this goes back to the notion of being able to respond rapidly right after an earthquake, particularly for facilities that have to have continuity of operations, whether it's a hospital or a fire facility or a business operations center, or a facility that contains hazardous material that you want to understand the integrity of. There are a plethora of applications where stakeholders would like to know about the health of that building right after the earthquake. And that's a task that in terms of a visual walkdown can take weeks or months, or can even be impossible in some sense when a lot of the elements are hidden behind architectural features and drywall. So this is a real technical challenge, but it's one that we think is very, very important. Our work here at UNR has been developing an optical sensor for measuring what's called interstory drift or deformation of a building. And historically, we've used accelerometers that some of you may be familiar with to measure the vibration of our building. And I would assert measuring the vibration with a vibration is not optimal, but it's the technology that's been available for the last 5-6 decades. What we are doing is taking a very low power laser. And if you think about a building deforming during an earthquake and you blow that up, and this is one floor, as that building shakes back and forth, that floor deforms. The columns twist and the beams twist, and you get a distortion or deformation of that floor. That distortion or deformation is a direct measure of the stress that that building has been subjected to. So you would like to measure that. Turns out that's a very hard thing to measure with accelerometers, to measure accurately. So we had the idea of propagating a laser across that floor and having a very specially designed sensor that is sensitive to where the laser is on that sensor. It can detect where that laser is hitting. And if you imagine this building moves back and forth, that laser that's mounted on the roof is going to shift relative to the sensor mounted on the floor. That gives us a measurement principle for measuring directly this interstory drift. So we take a laser, we diffract it and bring it down and impinge it on what we call a discrete diode position sensor. And this is just a grillage of a large number of very, very small light sensitive diodes. So we can measure exactly where that laser is hitting. So this gives us a technology, a new technology for measuring directly interstory drift. And we have gone through a spiral evolutionary design. This was the first sort of clues together generation 1 sensor that we cobbled together from various components. You can see the diode array here of the 3 diode set. We moved on eventually to generation 2 and then generation 3, which we built here at UNR, where we began to engineer this. Once we demonstrated that this would perform in the laboratory through extensive testing, we began to actually engineer a system that could be deployed in the field and was deployment ready. And you'll see here we have a communication node. We've skinnied this down to have a very slim and compact set of diodes, and a package here that all of this goes inside with recessed holes so we can use a very low power laser for that. That was generation 3 that we've deployed. Currently in the laboratory, we're working on generation 4, which will sort of be the end game or the final generation of this. And you can see this has a large number of diodes in there as well that the light comes down and shines on. But this is in 2 dimensions and it's biaxial. So when a building shakes, it shakes in 2 directions. This new biaxial sensor that we're going through proof testing on right now can actually measure the biaxial deformation of a building in 2 directions. So this is an intense effort. We're moving towards, frankly, commercialization of this technology and looking for partners for commercialization. And I mentioned at the start that when we do things like simulation and we do things like develop sensors, that's very synergistic with our experimental capability, and that's the case here as well. So I'm going to show you two of our laboratory tests. The one on the left is testing this on a steel frame structure that we're shaking under earthquake motion, and you'll see that vibration with these sensors on, so we can validate the performance of these sensors, and those sensors are on there. We showed that they work quite well. This on the right is the new biaxial sensor, and you can see the impinging laser light in a circular pattern now coming down and hitting that sensor. And let me see if I can start this over. The earthquake is going to hit. We're putting on earthquake motions that we got, guess where, from our simulation model. And you can see that floor jerk across on this 10-story building. And that is a realistic motion for a near fault earthquake. So you can kind of see, just imagine how you would feel that first pulse if you were standing on this floor in the building. But this laser, we're sampling all of these diodes 300 times a second. So we know precisely where this laser is hitting, so we can measure that relative deformation in that building as the building vibrates and this motion persists. And we are really, really pleased because we just got our first set of data from this, and Dr. Floriana Patrone is leading this effort, one of our new young faculty members, and the data is really, really good. So we're really excited about this in going forward. We've deployed 4 of the Gen 4 sensors in the Bay Area. Those of you familiar with the Bay Area, this is looking down at UC Berkeley and looking towards San Francisco. This is called Wang Hall at Lawrence Berkeley National Laboratory. It houses their supercomputer center. Wang Hall, unfortunately for them, resides right here. It's about 150 meters from the Hayward Fault, which is probably the most dangerous fault in the country. If you're familiar with UC Berkeley, the Hayward Fault goes right through Berkeley Memorial Stadium. So there's probably not a more important building that would benefit from having rapid real-time evaluations of earthquake response. So this is our crew from the earthquake lab here, deploying 4 of these sensors on our first trial deployment in this building, and we deployed them in 4 stations. These have been operational and running reliably since September 2019. The field deployment is important because once you validate the performance in the laboratory, you need to have these out in the field for an extended period to know how they're going to behave in a real world environment. Is dust buildup going to be a problem? Is laser diminishment going to be a problem? Turns out the answer is no. These have been exceptionally reliable and they're running today. We're waiting for our first big earthquake. The Bay Area usually has about a magnitude 4 earthquake once a year. These have been out going on a year and a half, and we haven't had a magnitude 4. So I was telling my colleagues we should sell this as an earthquake thwarting system as well, because we just have not been able to capture the first big earthquake. But it's going to happen. It's going to happen relatively soon, so we can get data in the field. We've also deployed our first outdoor deployment, and we've done that in Nevada in collaboration with the Nevada Department of Transportation. And this is on the Bowers Mansion overpass, going down 395 towards Carson City. And we put 1 sensor out there. And again, this deployment is very important because it's the first time we've gone outdoors where there's wind and there's dust and there's rain and there's snow. So we are in the process of monitoring and evaluating this performance out in the open, in the air. And so this is a very important deployment for us as well. And so far, so good, even in the winter. So we're getting outdoor experience there. So I'm going to end, and I'd be certainly happy to take questions. So these emerging capabilities, whether it's advanced simulation, intelligent infrastructure, or our new large-scale soil box, are really important to us moving forward and not being stationary. It's like any field. If you stand stationary, people and time pass you by. So we are working very hard and are very excited about these new capabilities and staying at the absolute cutting edge in our earthquake engineering laboratory and our faculty here at UNR. So with that, I'd like to, it's a whirlwind overview, I know, but I'd like to end, and I'd be happy to entertain any questions that you might have.
I've got a question to kick it off. When do you think you'll resume in-person tours?
That'll be dictated by the university. I guess I'm cautiously optimistic that in the coming year we'll be back on campus. Some of us have been on campus throughout. I teach my graduate course in person twice a week. All the appropriate precautions. And we had a little banter earlier. I'll tell you, my graduate students want to be in the classroom. I polled them, and to the 90th percentile, they want to be in the classroom where we can mix it up. And so I think that's great. I think it sounds like the university and, under state guidance is moving back towards more on campus in the fall. And so time will tell, but hopefully we're going to get back to a more normal environment in the coming year. And we certainly hope we can have you all in to stand next to our shake table in our motion box when it's moving. So hopefully next year. That's my hope anyway.
I had two quick questions. One is, does the type of dirt in your box make a difference, or do you have to change the dirt depending upon where you're testing?
Yeah, so the type of dirt does make a difference. We have our box qualified, if you will, for 3 different classes of soils. And I'll just say, weak, medium, and stiff. So we have the ability to look at different types of soils in our box. One of the operational features that we're going to have to work out as we start testing is how often, depending on the experiment, how often do we need to change out the soil? As you can imagine, changing out the soil in that box is not going to be a trivial task. And so we'll see what the cadence of the experiment looks like. But our current thinking is we can probably do, multiple experiments, depending on the character of the experiments, before we have to remove and recondition the soil and put it back. So time will tell. But the answer to the first question is, yes, we have a capability for looking at different soil types.
And the second question, did I understand correctly, the sensor system that you have, do you have to build that in when the building's being built, or can you go in and retrofit buildings and say, now we can know what the status of this building is? Great
question. We so far have retrofit, and we can retrofit. It's not that hard, but in our end game would to have these be built right into the structural system. And we're in discussion with Berkeley Lab. They have a new bioepic building that is going to be built over the next 2 years. They have agreed to place these sensors in that building, and we are getting in on the ground floor. So we are going to be very carefully for the next go round with Berkeley Lab, integrating these sensors into the building design. We have that opportunity. We're in early enough. We'd like to have these placed in the walls, as you can imagine, unobtrusively. And so we are hopeful going forward as this technology matures that these should be an integral part of the building design, and they can monitor continuously. And it would just be tremendous to have them be an integral part of the building. So that's our hope, is that we get to a point where they can be an integral part of the building.
Yeah, you showed the bearing plates and the precision for leveling. I'm assuming you're not using just a bunch of wood shims to level it out. What do you use as material for that?
Very carefully, if you look at each of those plates, there's a very thin layer of shotcrete type stuff below those. And so they place those very, very carefully and level them as they place them. And then they check the leveling once they're done with that, which is what you saw in that photo. And so they have a tolerance, and I don't know what it is off the top of my head, but they have to meet a tolerance for the levelness, if you will, and the flatness of those once they've done those. And if one came out bad, they would have to take it out and reset it. So they're very, very careful in setting those plates and making sure they're leveled from the get-go.
Hey, David, how far to create the movement, how far do the actuators move in any given direction?
Yeah, the stroke, I believe, is, it depends on the frequency you're putting in. If you're putting in a low frequency, long period motion, the stroke is probably a 1.5 to 2 feet, somewhere in that range. If you're doing high frequency, then the actuators are moving much more rapidly and the stroke is not as long. So it depends on the frequency of the ground motion you're trying to put in. There's a phenomenon called near fault motions. And it's come into clearer understanding over the last couple of decades. When you get in near the earthquake fault, because of the way the waves radiate off the fault, you can get these long displacement pulses in your ground motion. And we'd like to be able to replicate those in this system as well. And that requires a longer stroke by the actuators because the displacements associated with that are longer. So there's sort of 2 regimes of behavior we have to do. Our actuators have to be able to move very fast to put the high frequency in, and they also have to be able to move with a larger displacement stroke on top of that that replicates the longer, rolling type motion that you might experience if you're near an earthquake fault.
Dave, would there be any reason to add a triaxial measurement?
There would. It would be very, very challenging with that mass of soil. But there would. There's a couple of things that we did, based on just simply the practicality and cost of doing this. And one was to be satisfied with a biaxial table for moving that large soil mass. And the other one was, if you noted, I said it was 15 feet tall, the soil box. We actually wanted to do 20 feet when we originally started. It turned out to just be prohibitive by adding that 5 extra feet from a cost standpoint. So great, it would be great to have a triaxial table. And there's going to be a new triaxial table at UC San Diego for doing large scale tests. But with the mass that we have of the soil, it would have been very, very difficult and very costly in the design of this system to do that. But we can get, probably 90% of what we want to get from the biaxial motions.
Now, will you only be using dry soils, or will you do any mixing of liquids?
Yeah, that's good. Very good question. And as many of you probably know, when you have saturated soils, you can get into a phenomenon known as liquefaction of the soil. Because of the DOE mission and their interests, we restricted it to dry soils initially. What people can do and what one can do is to put a liner in the box and add water, if you can imagine, in a liner. And that's certainly a possibility in the future. But that's not going to be on our earlier list of capabilities. We're going to be primarily dealing with moist or dry soil initially.
Where do you get the soil, and does it matter whether it contains more than just dirt, if it has rocks and big rocks and things like that?
We only like good soil. So what we do is we go and look at all the vendors where we could get soil in Nevada and elsewhere. We take samples and we bring those into our lab and characterize those soils very, very carefully. So we do sieves to get fraction passing a certain size, and we do tests on those because we really want to identify a reliable vendor of high quality, well-graded soil. And so we're in the process of doing that right now as we speak. We're testing a number of different varietals of soil. So we want to be very discriminating in the dirt we use, right? and make sure that they fall into the classifications and the characteristics of our soil that we've qualified the box for. So there's good dirt and bad dirt, and we only want good dirt in our soil box. So we're very careful with that, and we test it extensively so that we understand what we're putting in there.
I know this is not your field, David, but it sounds to me like for places like California, and maybe even if someone was talking about Yucca Mountain or something again, that this would be a requirement to put into buildings because of the safety factor, especially the taller buildings that would house more people. I think of things like that building in San Francisco that's already tilting.
Yeah. Well, we don't disagree with you. We think that this would be a very important technology to have, particularly in an urban setting like San Francisco and Oakland. People learned in the Loma Prieta earthquake how challenging it was to validate their buildings and the health of their buildings, just from the standpoint of human capital and not having enough engineers. And you can imagine if we had a Hayward Fault earthquake or a San Andreas earthquake adjacent to San Francisco, the recovery time would be tremendous. And we think that having these sensors deployed so you could get very rapid data on the building and what that building experienced would be very, very important. We're having some discussions with some folks from Japan about commercialization of this technology. We have 4 patents on this technology. We have a US patent, we have a US patent pending, we have a patent in Japan, we have a patent in China, and we have a European patent that is registered in Italy and Greece. So the intellectual property is out there, and we've just got to find the right commercial partner that will help move this forward with vigor and expeditiously. So we're looking forward to the transition of this to practice, and the field demonstrations that we've done have been important to that. But we really need to, when you go and start to talk to commercial entities they want to deal with a commercial entity in terms of deployment, that they can have, professional standards and hold accountable for the deployment. So that's going to be important to widespread adaptation of this. We can do the research, we can do the demonstration deployments. We really need a commercial partner that will spearhead the broad scale marketing and deployment of this technology. So I think that's the next step.
Hey, David, this is Marty Potnick from Nevada Industry Excellence. We work with manufacturers all around the state. I'm very curious as to if there's been interaction with Bentley, Nevada, who are worldwide known relative to vibration technology in a major scale, and if you all have ever had interaction with them.
Martin, the short answer is very little. We've had a tangential discussion when they were on campus pre-pandemic, but if you could help us make a connection, we'd love to have a dialogue with them.
Sorry, what I was going to say is I think it's right up the alley of both avenues of what you're doing with highly respectable research, as well as their respectability internationally on vibration technology.
Yep, not a bad idea. And we're really at that phase with this new biaxial sensor that we need to, find a way to engage those robustly.
And I think also too, timing might be right, because I believe, I don't want to speak for them, I don't know if anyone's online from them, but I think they're also looking to expand outside of very large vibration technology. A lot of it was generators, very huge complex structures. From what you're talking about, I think it's up the alley, so to speak, of both your interest in what they do.
Yeah, great.
Now, plus it's homegrown, which we all would love to do for Nevada, right?
Sure.
Well, David, thank you so much. That was fascinating. And we hope we can take you up on your offer to come visit you in person.
Absolutely. Anytime. And thank you for the opportunity. We always like to share with the community what we're up to over here in our laboratories. And we really appreciate the opportunity. And thanks again so much.
You're very welcome.